but still did not get time to schedule it on the convenient like evening time. So this is the way. Okay. So first start off with let me introduce myself. I have worked in VLSI for around 9 years right now. Currently, I'm associated with Synopsys, but before that, I have multiple experience with Intel, MediaTek, and on Semiconductor. And most of my role falls into DFT and post-silicon validation. So right now, I'm kind of managing three people in Synopsys, and uh, that's all about me. So is it fine if everyone introduce them? If everyone on the call introduce themselves, so that I get to know whom I am talking to.
Yeah,
Hi.
myself Vinod.
Okay.
Currently, I am working in automotive domain. Earlier, I worked in hardware and embedded systems like products.
Embedded system, is it?
Yes, yes,
So,
embedded.
do you work in VLSI or I mean, uh,
VLSI means when I was working for defense projects, I used to work with FPGAs, Verilog and VHDL programming.
okay,
Not much. I have 1 2 years of experience exposure on that.
okay. So right now you're working, right, Devi?
Right now, I'm working in automotive domain.
Okay,
It's a kind of system testing.
okay. So may I know any specific reason you are like interested in validation, or it just like may I know
So
the intent?
yeah, earlier in automotive domain also I worked as a V&V verification and validation. So
Okay,
I thought this is a continuation to me as I know I have experience with hardware and FPGAs and microcontrollers. So I feel this is the continuation kind of thing. So post silicon validation also.
okay, understand. Yeah. Nice to know.
Yeah, thank you.
Maybe someone else, Lokesh or Rashmika?
Yeah, so I'm Aishwarya. So I'm currently working as a hardware automation and validation related activities. I'm working. So I'm working in IBM, and it's been 2.5 years I've joined IBM. And so mostly I've worked on the automation related works, and it's about the memory validation, validating the DIMMs, DRAMs, those kind of works. So now I'm interested in more about, because this is somewhat related to the post silicon, as after the chip manufactured, like the DIMMs, that is like post silicon. So that's what I'm working, right? So I want to know about how the post silicon validation of the chip or processor works. So that's the main reason.
Okay. Understand. So you're working on SRAM validation, is it, Aishwarya? DRAM. Okay.
No,
Okay.
DRAM.
Okay.
Yeah.
So right now you're into data analysis, mass production, or which phase of experience you fall into right now?
I didn't understand. Could you
So,
repeat?
so for the current work that you're doing at IBM,
Okay.
uh, are you into bench validation or ATE tester or a data analysis? Which automation?
So we don't use any instruments. So it's like just validating or qualification of the DIMMs only. It's about.
Okay.
So
So do you?
like, yeah. So generally IBM has a servers, right? The product they produce is servers. So at
Mhm.
last, so after the chip and all processor everything works, then only we'll start our validation of the DIMMs, the memory that is present in the system.
Mhm.
Yeah.
So on server means you must be well versed with the firmware and all stuff.
Yeah. Not well versed, but I got to know like firmware also. Yeah.
Okay. Okay. Understood.
Yeah.
Yeah.
Thank you.
Lokesh. Yeah. Thanks, Ashara. Thanks for the intro. Lokesh or Abdul.
Logesh is only the candidate. Logesh, Aishwarya, and Vinod.
Oh, okay.
Only three
Okay.
candidates.
I
Yeah.
see Abdul also. Abdul is kind of
Actually, he just joined. He's working. He's right now learning RTL design engineer. So he just joined to understand the things only.
understand. Understand.
Yeah.
Okay. Fine. Okay. So
So, yeah, Logesh, can you please introduce yourself?
Sir, I am Lokesh. I am working in Foxconn HANA department as a testing engineer. I am working in a mobile phone with handling failure analysis and automation, including I am working in fully on testing fixtures, handling fixtures like DFU, AP testing and RF testings. Working on fully on I have a overall 7 years experience in EMS testing. EMS is nothing but electronic manufacturing services. Uh, and I have experience in debugging failure analysis, and I also have experience with automation. I need to know about what are the validations to develop my skills in that's all.
okay, okay, understand. Yeah, thank you. So let's keep it interactive. So I would, I think, can you please mute your? Yeah. So I hope I'm audible. So let's keep it interactive. So I think you people, all you guys are experienced. So you can put up a questions whenever you need to. I mean, you have a doubt, but I would request you can hold off your question for 5 minutes until I complete the presentation. I will point out when there's a slot where you can ask your questions. Is it fine for everyone?
Yeah, fine. Yeah.
Okay. And is there any specific thought you have in your mind before we start the presentation? Like, what do you wanted to learn? I wanted to know that. I understand everyone wanted to understand what steps are being followed. Okay, let me put it this way. So, what I understand till now is you have questions with respect to how the validation flow is, how to understand it, how to make, uh, uh, how do you validate any test shape, or how do you validate on bench or AT? Is there any specific constraint or understanding people wanted to have, or it's like general validation flow people wanted to understand?
So actually, the thing that you're mentioning, right, like bench validation, that itself, maybe I'm not aware. Maybe those and all, that is where we need maybe a basic also.
Okay, okay. So, are you guys aware of what the VLSI or ASIC flow is, or should I just brush it up just to make you aware of it? Maybe Aishwarya, you might be aware, but
Yeah.
the question is specifically to Devi and Lokesh if they wanted to understand that. Uh, Devi Prasad and Yogesh, do you have some?
Sir, I am completed diploma in EC, sir. I'm not. I have a little bit experience in what are the embedded and VLSI.
Okay, so you have understand basic understanding, but it will be better if I brush it up. Is it okay to say, Lokesh?
Yes, sir. Yes, sir. Okay, okay.
Okay, fine. So Aishwarya, it might be repetitive for you, and I'm not sure if Devi Prasad have some feedback on this, but I will still brush it up on the basics of VLSI. Okay.
Yeah, sure, sure.
Okay, sir. Okay.
Okay. So you can call me Piyush. Sir is kind of sarcastic way of pronouncing it. You can call me Piyush. Okay. Fine. So I have created a small presentation on what exactly is the post-silicon validation. What are the steps involved in it? We can jump into that. But I'll give you a slot to ask questions. Meanwhile, I'll go through the slides. Probably that will help you understand what exactly the VLSI flow is. Okay. So
Both you were okay.
So mostly my work falls into DFT, sorry, the validation, but from the DFT point of view.
Okay.
So I will explain you what exactly validation is and where my role falls into.
Okay.
But probably I have better understanding on in terms of bench validation, tester sequences. So that will help you understand what exactly is the VLSI flow, and probably that will put up more lights on what the VLSI, the silicon validation flow is.
Okay.
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 Okay, so let's start on this one. So basic diagrams, right? So this is the diagram which shows 7 sequential stages left to right with arrows indicating each boxes. The first 6 stages are dark blue, which are pre-silicon stages. So basically ASIC flow, very large scale integration. So this is what ASIC falls into. But anyone knows what ASIC is?
Application specific integrated circuit.
Yeah.
Sorry.
Application specific integrated circuit.
Yeah, but what exactly it is? And I understand the basics. So let's not talk in terms of very the abbreviation or expansion kind of thing. Just talk in terms of what exactly you understand. What is exactly ASIC? If I ask you what is the um, simplest
Like
term ASIC you have in your life?
integrated circuit for specific application means kind of that we called in aerospace. I seen some specific microcontrollers. They designed for particular application. It's not for general microcontroller.
Okay. So again, it's again abstract. Your answer is right, but the thing is, ASIC is basically if you wanted to understand the simplest ASIC, right? It's your calculator. Okay. So calculator is a ASIC design which is specifically made only for computation. Okay, now you can scale it up to the level you want. You can have a specific design that works on, let's say, go to Mars, capture an image, and send you back. That is also ASIC because it is made specifically for that purpose. So the same chip, if you put in maybe your laptop, does not work as expected because it is made for specific application. So ASIC is basically that. So it is made for specific application. Okay, so VLSI and ASIC both refer to custom silicon. It might have billions and millions or billions, so transistors in one die, and designed only for. So ASIC is basically designed specific for specific product rather than general purpose catalog part. Okay, so this is the basic diagram that everyone I wanted to have. Have it mugged up basically. So I mean we will later discuss the different steps, for example bring up what is functional validation, but everyone understand, I need everyone to remember this, that we might come back here and might refer to some definitions here. So I wanted to spend some time on exactly what is the ASIC flow. Okay, so, so what is specification and architecture, right? The first step here. You're able to see my pointer? Uh,
Yes.
Yeah.
okay, okay. So what exactly is specifications, right? Anyone have brief idea? Just give me. So as I said, right, ASIC is basically a calculator. Can someone explain me what specification and architecture is? Just one simple word.
Maybe the problem statement or the need.
May not be the need. Need is a requirement, right? So I wanted to have something to calculate is a need, but a calculator is an application. So a calculator is a design that serve your need, right? So that is what specification comes from. Specification is what I wanted to do and how my design will be. Architecture is how exactly my design will look like. Okay, so this is the first step which we must do before we write any RTL design. Okay, we'll come to RTL design. It's just like whether you write before writing any code, you should know what your specs are and probably work on their architecture, how we will achieve those specs. Okay, so the output. So what? Okay, do you know what output of specific and architecture structure is? So before you give a try on RTL design and coding, right? What will be the output of uh, a specification and architecture? Just a brief view. Anyone?
Maybe from my concept, I would say specification, it's a PDF or document, or architecture, it will be a diagram, or maybe.
Yeah, maybe correct.
So
So
what kind
it
of interfaces is required to communicate each block to block? Those kind of.
yeah, exactly. You cover all. So basically, output of the specification includes microarchitecture document. It includes the interfaces. For example, are you going to use AXI, PCI, DDR, and what are the feasible models that you will have, right? Uh, this is very important step. Do you know why? Why can a specification and architecture important step? Just a take example of a calculator. What will go wrong if your architecture is wrong?
I think entire design will go wrong, right?
Yes, exactly. So once you miss something here on the specification architecture, nothing can fix in this. So your RTL code won't fix it, your functional verification won't fix it, your synthesis, DFT, tape out, and the post silicon validation, nothing will work if your architecture is wrong. So this is very basic where people spend a lot of time to understand what the market requirements are. They design the architecture and then people. So however expert you are in, let's say DFT or STA, if your architecture is messed up, nothing will work. Similarly for other stages as well. Okay. So the first golden rule. We are looking for this orange box, right? Post silicon validation. Everyone should go through the specification and architecture before you even start thinking about validation. Okay, because this will help you understand what exactly a silicon will perform on field, right? So for example, a lot of people are from automotive. If you wanted to have a camera sensor in your automotive device, right, you need to have all the specifications for it by heart. Then only you should touch the post silicon. The first step, you should mug it up, because you should know what the expectation from the silicon is. So post silicon validation is nothing like, it's not like somebody says, okay, RTL team says this is the architecture, validate if this camera sensor works as per expectation. No, does the camera sensor in the automotive that I'm applying works as per the specification, not as per the RTL, right? That's the so this is an important step. I wanted to spend some time to give an emphasis on what is the importance of specification architecture in the VLSI flow. Okay, so that's about the specification. So once you define the specification, once you come up with, okay, this is how my architecture will look like, right? You will uh, give a block diagram, as I said, the document, right? The micro architecture document that will include the how your design will look like. Now, the next step is to RTL design and coding. So I hope many of you know what exactly the RTL is. Can someone just put it up? What exactly does RTL mean? So people have worked, right? So they must have heard the RTL design, right? What exactly the RTL stands for?
It's a high level programming language, whether it's a Verilog or system Verilog.
Exactly. So it's a register transfer level. As you said, we know that it's high level transistor language. Usually people define it in Verilog, use system Verilog. There are few unpopular like VHDL language, which also does the same, but it's more complex, less flexible. That's why people have discarded and moved to Verilog. And as people have moved to Verilog, Verilog has become more, popular language basically. Okay. So what is output? So when I say, okay, this RTL and coding part, what is output of this RTL? Does anyone know what this stage looks out, which man says, okay, this is the calculator, but if the post silicon engineer does not know what exactly to understand from the RTL, right, then that document is very important. So VDC, which is clock domain crossing, me just briefly go over, because time is a constraint. So probably let me go over the functional. So what exactly RTL gives is a RTL team gives a logically correct and simulated waveforms for formal method, which might be emulated or simulated or both. Usually it is in the form of UVM, which is universal verification methodology, which is like with constrained random stimulus, and this is a UVM is industry standard. Okay, so this is what the functional verification team will take in, and this again involves billions of waveforms. You people might have seen the wordy waveforms, right, where people will analyze the this signal goes up, that signal goes down, right? That's something which happens in functional verification. I think Aishwarya and Vinod might have seen it, but Lokesh also might have an experience on it, right? Okay, so once the design is verified, right, that goes into the synthesis and placement, route placement. So this part comes in the physical design part. Okay, so as I said, the RTL is synthesizable netlist. This synthesis, so post the design is verified, sorry, it comes into the physical design stage. So uh, what do you understand when you hear of the term physical design? What could happen in this stage? Can anyone try?
It's a routing between the.
Yeah, that name indicates.
Yes.
Lokesh or Ashwarya, do you want to give a try on what exactly synthesis and place and route would do?
So this synthesis and place route is similar to physical design, right?
Yes.
Okay. So it's like placing all by virtually they'll place all the components where it should be, right?
Hmm.
Be the what they'll say is that IP or mic something they'll say macro, or so that one they'll place everywhere, and uh, so I'm not able to tell that, but it's like they'll place route. That's what, right? Route. So how it should be communicated within the two IPs,
So
maybe.
basically, till this, yeah, understand. That's a partially right question answer, but let me put it in formal words. Okay, till this point, right? Functional verification, everything is in terms of code. No one, there is no nothing in terms of how exactly. So it's just like a switch, right? How you draw a switch on paper, you just draw two lines and a flap that comes when it is connected. It is on. When it is disconnected, it is off. That's how you write till this point. But in case, so what this routing does is it actually imagines how two wires will be placed, and how what is a mechanism that pulls that wire down so that the switch can be closed or open. Okay, till this point we haven't thought of how the physically uh, the RTL will be converted into that into the real silicon, right? But here we do the actual placement and routing. So as I said, it's very rude example of saying that wires are connected and the switch that connects it. But in terms of silicon, I mean, in terms of VLSI, it's like gates connected. They are placed across the silicon, and how your, so it's not like a AND gate that we fabricate. It's like billions of gates that are present. So how the connection from one flop to other will go, which layer that will cross to, and then all these things will happen in this placement and route state. And this next step that, basically this is like tools which are like design compiler, Innovus, which will come into the picture. And the idea of having this placement and route is to have optimal timing, area, and power. So always silicon terms, people will talk in terms of uh, PAT, power, area, and timing. Timing should be minimum, ideally, depending on the device. But yeah, if it is minimum, then people are, all your specifications, right, are defined in terms of power, area, and timing, which this VLSI flow tries to understand. Okay, this will include wire delays, because as you are placing the flops to one another, right, there will be a the wire that goes from one flop to other. So that will have wire delay, congestion, crosstalk area, and all those stuff come in. And the important part is how you imagine a circuit to be till this point may not behave after you do this physical design. Okay, because there are variables that will come into the. That's what the job of post silicon validation engineer is, right? Whatever inefficiencies or the discrepancies that you have in the design, identify those. Okay, so we are like gatekeepers. If you say that okay, I have a valid ID card, I should go in. But if you slightly doubt, okay, the ID card does not match or name does not match, stop that candidate, right? So that's what the post silicon validation engineer is. Okay, okay. The next step is DFT insertion and STA. So I have placed them together after PD. I could have put the STA in physical design, but I did not. Do anyone know what DFT and STA is?
Yeah, design functional. Sorry, DFT is a static time analysis and
Correct. STA is static timing analysis. DFT is design for testability.
yeah, design.
Okay. So now imagine you have like lakhs and crores of transistors one after the other. Now, let's say you have fabricated a silicon. There are multiple ways silicon can fail, right? How do you identify them? So we insert DFT in the design so that you can generate a pattern at a specific place and identify where the issues are, right? So that's why you have DFT insertion and STA. So STA comes in here because see, what is static timing analysis? Does anyone have brief idea of why it is static? Lokesh, maybe? Or Vinod, whoever knows.
Static timing analysis generally we define for delays, delays between the data flow.
Correct. Yeah. So it's like yeah, partially correct. But yeah, I mean, once the physical design is done, you put a wire between let's imagine a two cascaded AND gate, right? So one is two input AND gate, output of that AND gate goes into the next AND gate, right? So you insert design for testability and make sure that your timing doesn't break. That's why STA is placed after DFT insertion. Okay, so that's all it is. And I mean, the next step after DFT insertion and STA is tape out and fabrication. Okay, so uh, I mean, tape out in the sense your silicon comes out, you deliver this DFT and STA design to. You must have heard the term called TSMC, right? So we give the GDS to TSMC or any other fab manufactures it, give it out, and that's how you get the silicon to test. Okay, so this tape out is so irreversible handoff. Okay, it's not like okay, sorry, there is an issue, we will fix it. Once this goes out of your hand, then it is done. There is no looking back from here. Okay, so all this should, so if DFT finds a issue, it will point it to maybe RTL design, RTL will fix it, it will go through verification, then synthesis again, DFT will check if it is fixed, and then only will tape out happen. Okay, so this is the overall flow. And after your silicon goes out, right? So usually like 10 years back, people used to think that okay, all the companies will have their own fabrication unit, but that's not the case right now. There are few companies like TSMC, Global Foundries and all stuff which does the fabrication. So this comes here, right? So the overall cycle is around 2 to 3 years. Okay, and once you get the silicon in post silicon validation environment, that is where our role of a post silicon validation engineer comes in. Okay, this is the overall flow. Anyone have doubt?
So I have a doubt. So actually, in our company, we have a exerciser team also, which does like simulation. So that one comes under where?
So see, once you design the RTL, right?
Okay.
RTL needs to be simulated. What exactly is simulation? What do you think what simulation is?
So it's like without the actual one, they'll use as a virtual with inputs for the test.
Did not get. Can you elaborate?
So without actual, maybe a silicon, they will keep it as like a emulator kind of thing, and then they'll do the testing.
Not really. So simulation basically is so emulation and simulation are two different things. Okay. So see, simulation is, let's say, just imagine in terms of, don't consider in terms of tool how it does it. Okay, tool will do it on its own. Let's imagine an AND gate. Now you wanted to have one as an input, output of that AND gate. What is the input that you will give? Both the
One.
input should be one.
Yeah.
So that's how verification will work. Okay, if your AND gate you pass two inputs as one, your output should be one. That's a verification step, right? But simulation, the verification in the sense, verification is simulation. So after RTL, simulation will come in all the places. Okay, but mostly simulation, when we say UVM, right, it comes from RTL to functional verification. Okay, where you will simulate that. Okay, if I give two inputs, does the output comes as one, right? So here is where simulation will comes in. Okay, now the emulation is a different thing. Emulation is, let's say, you wanted to test it, right? So for example, imagine you have just imagine you being a child, and you know till 10 only. Okay, now uh, 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 you wanted to add 2 plus 2, right? That is under your limit, so you know 2 plus 2 is 4. You go to 5 plus 5, you go to 10. But as you don't know, 5 plus 6 is 11, right? So emulation is putting it into a higher. So what you will do is you will go from third standard to fourth standard, right? And you actually test, you understand first what 11 is, and then you try to put in 5 plus 6, right? So on real silicon, you put so imagine a calculator, right? Now your calculator does have only uh, uh, I mean, it can do a computation till 100. So 50 plus 40, 90 can be displayed on a calculator. But somehow you imagined, okay, there can be numbers like 60 plus 60, which goes beyond 100, right? How do you, or goes beyond 100? How do you emulate it? So what you'll do is you'll put it in a higher system. We can compute it. And then, I mean, before running it on silicon, you test whether a logical understanding works. That's what emulation is. Emulation is tested on actual hardware. It's not assuming that if you pass in two ones and get output will be one, right? So that's what emulation is, right? So then we come into this step.
Okay, so emulation, I hear maybe it's not because you mentioned right actual chip they'll test.
Yes.
Okay, because I heard from our company, it's like exerciser team. They'll does pre-silicon and both post-silicon also. So
Yeah.
pre-silicon also, maybe have you heard of the team exercises?
Yes, I know.
Okay, so exercises will both do. Sorry, will do both pre and post-silicon, right?
No, exerciser will do it post silicon only.
Okay, maybe here they are doing because this is a server. Maybe you have worked on server or mobile.
Both. I've worked on all the things that you can imagine. Okay.
Okay.
So yes. So simulation is, let's say, how. Okay. I mean, Vinod might be aware, right? How do you uh, dump a AND gate on FPGA? Have you heard of it, FPGA, Ashwarya?
Yeah, I have heard of it.
Okay, so simulation, what it will do is it will transform your FPGA into a logical operation, so that you can actually program that FPGA to perform as an AND gate. Okay, now to do that, to do the burning of your test code on FPGA, you do simulations. Okay, so what you're referring to, right? Exerciser, pre-silicon and post-silicon. The part that I've explained is pre-silicon. Okay. Now, uh, Vinod, you have some question?
No, Bish. Okay.
Okay. So this is what pre-silicon is, right? Now post-silicon is once you have dump your FPGA code on FPGA and now your FPGA behaves like an AND gate, right? Then what you do is you pass electrically 1 and 1 on the two inputs of AND gate and see on the output of an AND gate do you get one. Okay, so these are like pre-silicon and then post-silicon of an exerciser, which is emulated, not simulated.
Okay. So
So
here exerciser meaning, what is the meaning of the exerciser? Like,
exerciser is basically whether you are able to your hardware, right? So imagine an AND gate. Now AND gate, you have designed a RTL code which is functionally verified. You have passed in simulation. You have passed in two inputs. It is giving output as one. You have synthesized the design, and then it's not like you just define an AND gate, right? You can have multiple designs, but you just wanted to see whether if I program that hardware as an AND gate, does it work that way? Is my design of an AND gate is correct that I have coded in the RTL, right? So is that correct? That you need to verify on the silicon, right? So silicon, when I say it is it needs to be tested on silicon. So silicon does not only have AND gate, it might have OR gate, it might have NOT gate, it might have multiple gates, but you wanted to test your logic for AND gate, right? So exerciser is a complete FPGA block which can emulate your design so that logical uh, the logic that you have derived in the RTL can be verified or emulated functionally. So exercise is in hardware.
okay, yeah, got it. Thank you.
Okay. 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 Fine. So let me just go over the. So I think I have defined everything here. One minute. Give me a moment. Okay. So what is VLSI? So it is designing chips with millions and billions of transistors. Okay. So uh, as you see from the previous thing, right? It's not individual game. So if you are good at RTL, doesn't mean your silicon will work, right? If you're a good DFT engineer, doesn't mean your silicon will work. Or if you are, let's say, if you're a good specifier, okay, I wanted to send my chips to maybe some other planets other than Mars or some other planet, right? It will work. Doesn't work that way. It's a team effort, right? So everyone has to perform their activity so that the post silicon engineer can perform his activity and confirm that whatever is defined works as it is expected. So it's a team sport, it's not individual game. Everyone needs to contribute um, uh, and then their part, deliver to next step, and then a next step has to perform, and then eventually you will get a silicon which is works as expected, right? Okay, so this is, I think, all the flow I have explained previously in the previous slide. So typical life cycle of a product, it might vary from 12 to 30. It depends on how complex your product is. If it less complex product, less complex in the sense, it doesn't mean low value, right? But less complex in the sense the product which are known, we know the issues we have. For example, mobile phone. If you think in terms of designing a mobile phone, right, it's very difficult task to do. But once you have designed enough of mobile phone, you know what issues can come, so your life cycle can be reduced. But let's say you are, for example, SpaceX is sending a chip to Mars, that no one knows what the issues are, right? So it might take longer time. So but usually for any product, right, coming from specification to the silicon usually takes around 12 to 36 months, 1 to 3 years. Okay. Okay, let me just, so this is like, as you see from the this one, right, it's like requirement will go to design go to pre-silicon verification will goes into tape out, where STA I have drawn in a circle to show that everyone's role is important. If let's say fab does not work, nothing of your design will work. Or let's say design does not work correctly, everything. So it's circular life that everyone needs to perform their role, then only silicon will work. Okay. So I think that's all I have right now. There are like multiple slides I have. Probably I have created some no, 100, 200 slides, but this is what I have for today. I'll stop for here for any questions, and probably these will be the topics that I'll be discussing in the next.
Yeah. If you have, can you show me the what is the syllabus you are going to cover in this course?
So maybe I think you will get it in a browser where the modules will be discussed. I don't have it handy right now, but maybe uh, you will get it from the 1 second.
Yeah, sure.
You'll get it.
I will share Pius.
Yeah, yeah.
Okay.
Can you please share that? Okay.
Yeah, no problem.
So
And
I have
Yes.
designed
last
full
question from my
course
side, Pish.
on all the modules that I have that are there in the slides. Okay, you can go through it and probably we can come back here again. Okay.
Sure, sure. Uh, when we compare with the DFT with post-silicon validation, uh, how much is the common subject percentage wise? Means kind of
Can you come again? I did not get the question.
when you compare with DFT and post-silicon validation, generally, how much the common subject, the common topics to
It's
learn?
not common, so it's niche in its own way. Okay.
Okay.
So it's not like DFT can overlap. So it's like just saying in a cycle how important is the paddle. Paddle just rotates, right?
Yes.
It doesn't do much, but cycle won't work if your paddle is not correct, right? So that's how it is. It's not like overlapping or common subjects, but they help each other to make thing work.
Okay.
So once you understand the overall VLSI flow, right, then you, as a post silicon engineer, it's not like my work is better or RTL designer is better or physical design is better or DFT is better. In terms of understanding, right, you can have your inclination on interest of subject, but everyone's role is important. Okay. So and everyone has their niche expertise that other domain cannot have. So what DFT understand, physical design does not understand. What physical design understand, RTL team does not understand. So every it's not very common subject, but at the end of the day, your job is not to be expert in physical design. Your job is to get the product out, right?
Yes, yes.
That works. So it's more of handoff between two three things. So DFT will provide a collateral. So DFT and post silicon validation, it's there are a lot of common things, but those will come in when you debug something.
Yes.
And you need a specific DFT architecture to be used,
Okay.
right? So so every subject is common. Verilog basic thing everyone should know, right? But it's of that sort.
That's it. From my side.
Okay. Any other question?
Yeah, I have a doubt. So you mentioned, right, you're working on DFT and both post silicon validation.
Yeah.
So I would like to know what kind of work that you have done or doing on post silicon validation.
So actually, I'm working on ATE as well. So ATE simulations, running the sequences, generating the sequences, which runs on silicon, verifying the silicon, validating the silicon on test chips. I've worked extensively on ATE testers, where the test program will execute the functional patterns that will run and pin those into specific pass or fails, then do the yield analysis on those. I have used the DFT architecture to identify in the design if your, let's say, if you're working on CPU products, right? It if your clock does not work, then nothing will come out. But there is a way that you can extract the information from the flops, which are existingly at a halted stage. You can map it to resistors, identify what exactly caused that halt. So I've worked on that. So there are multiple domains I've worked on, which is kind of both DFT and post silicon validation related.
So from my perspective, I know that like post DFT is a part of post silicon, right? Post silicon validation.
No, DFT is a part of RTL.
No. So DFT, I think So DFT own comes under. You mentioned that pre-silicon they'll do, but post-silicon also they'll do, right? With the actual one, they'll check the whether like AND gate you mentioned, right? Whether this is same something they'll do it in post-silicon as well, right?
So see, yeah, everything is tested in post silicon, right? So your
Yeah.
RTL is also expected to work, right? So RTL is implemented on physical design. So physical design is also tested in post silicon. Your physical design has been verified. So verification also works in on actual silicon. So ideally, whatever you have specified in the first place, that okay, my chip will work at 10 gigahertz, let's say, irrespective of what stage. RTL has designed some way, physical design is implemented some way, DFT has inserted the DFT architecture in it, verification has verified it, and then synthesis team has synthesized it. At the end of the day, everything will get tested on silicon, right? So DFT, physical design, verification, everything get tested on silicon, and your
Yeah. So
assumption is everything will be verified.
yeah, so that's what we call it here as bring up team, which does the post silicon validation. So I would like to understand that the so maybe DFT, I would say as of now it's maybe both the pre and post. So other than DFT, like what are the main teams or you worked on the domain on post silicon? Maybe
So
name
I,
the.
I have worked on ATE, I have worked on DFX. DFX is DFT architecture used for post silicon bring ups. I have worked on multiple, around 8 silicon bring ups till now. At current organization through ATE team, we have done the validation of test chips at Synopsys. We have done in DFD domain. So there are multiple domains I have worked on.
Okay, so in bring up, like what are, how do you like what you have done? Could you like maybe overview kind of?
Bring up in the sense, see, you have to define what customer use cases, how the so currently I'm working at Synopsys at a service IP level, right? We deliver IP where customer takes it in, put it in the silicon, verify it, right? Or validate it. So we give them the sequence uh, that once they integrate at SoC level, they should be able to test the IP that we deliver. Okay.
Okay, it seems you're working on pre-silicon, right?
No,
No, you're
80 is
mentioning
pre-silicon.
IP, right? Yeah. So no IP. So after you give the IP, then they'll fabricate. Maybe I thought that's a pre-silicon one.
No, it's a post-silicon one. So once you deliver the IP, it comes into silicon, and then you need to test the silicon, right?
Yeah.
Using function. And so bring up team is that only, which bring up team gives you a sequence that will work on the IP that you have delivered.
Yeah, that's true. So
Okay.
because now what I'm looking is I need a mentor where he or she should guide me, because now I'm working maybe a related post silicon, but not about maybe not about that VLSI or ASIC workflow, right? So that one I'm not part of it. So I want to know. So maybe learning is also one thing, but they people should or trainers should guide me regarding the mentor. So how what are the next plans in my career? How should I move forward from this career to the next career, like post silicon validation, like that also I'm looking. So is that possible?
Yeah, obviously it is possible. And so see, uh, as a what I would recommend is, instead of looking for mentor, right? You
Okay.
should come up with a question that you have. It may be
Yeah.
a basic question. So
Mm-hmm.
instead of me asking what you have worked on, right? If you have a question, what exactly bring up
I,
team does, I would appreciate that. That will
okay.
give you a idea on what you need to work on, not on what. No one is handholding you.
That.
What you worked at IBM, I have no idea, right?
Okay.
What I worked at Synopsys, no one in IBM have that idea. Correct.
Mm.
So it's not like somebody can handhold you to a domain. People can give you enlighten you on what exactly steps they follow. So if you do what I did, you will not get what I got, because you are in a different company,
Mm.
right? So imagining that I will handhold you on everything will be a incorrect explanation or incorrect expectation. But I
Okay.
understand that having a diverse opinion or having a diverse experience will help. I appreciate it, but no one will give you a direct hand holding on. Okay, now I wanted to switch. What should I do? No, you keep building your ideas, keep
Okay.
thinking, keep understanding the exact silicon behavior, why you do what you do, and then probably you will land up in the domain and you will never know, right? So I would say that way.
Okay. Okay, so have you worked on like memory or PCIe protocol related validations or?
Currently, I'm working on PCI validation.
Okay. So PCIe like so it's a post silicon or pre silicon?
That's,
Maybe
I mean,
I'm not. I don't know. That's why I'm asking.
uh, both.
Both. Okay.
So see, what you are asking, if you have a calculator, does your calculator do multiplication, addition? Is subtraction a part of a calculator?
Yeah. Abstraction.
Subtraction, right? On a calculator, do you have
Subtraction.
minus sign?
Yeah. Yeah. It's a part.
Yes. So whenever there is a communication between two ICs, right? There is a protocol. PCI is a
Mm.
protocol. Now, RTL design will code that protocol. Physical
Yeah.
design will implement that protocol. That's the
Okay.
pre-silicon part.
But the
Once the
verification, yeah, yeah. So, but both has the PCI link, but the verification varies, right? The post silicon we will test actual that PCIe. So, but for pre silicon we don't.
we
Maybe.
test actually everything, okay,
Okay.
but there are scenarios which you cannot replicate because simulation is not very easy to do, okay.
Ah, that's true.
Validation does 1 second for a job, simulation might run for 2 days to emulate it, okay.
Ah,
I mean,
that's true.
so it's not like all the corner cases you can run. You can't take 10 years to come up with a mobile better than Nokia, right?
Yeah.
Till that time people will go beyond your reach, right? So it is important to be within the specified limit, and then you verify minimum that is possible, but you validate everything that is possible because validation is fast.
Okay.
Anything else? Probably we
Yeah.
are.
Maybe for post silicon, like what are the topics that you would recommend?
uh, yeah, I will I will give you the I mean, team, mute yourself. uh, Yeah. So Jasttech team will share you the modules that I'll be covering. Okay. That you might have a look on it and then see the topics that you will see in the upcoming classes. Okay.
So no, not about the upcoming classes. Generally, I'm so maybe I would say from my concept, my perspective, like computer architecture is very important, right? For this VLSI field, and then like that, I'm generally about asking like registers, memory, so protocols. So these are like important, right? So before knowing to this post silicon validation, we should know the basics, right? So that's what I'm.
So CPU architecture is important, but the team that I worked on does not spend any time on CPU validation. Okay. So it's not like you can't cover everything in one plate. Validation is a vast domain. So when you validate a calculator versus when you validate a chip that goes into space or when you validate a chip which goes into PC, right? Everything has a different scope to validate.
Yeah, so that's
So
like a domain. I'm talking about like the basic need for the VLSI domain. I'm asking. Maybe that does.
basic need for the VLSI domain would be you should be aware of protocols. You should be aware of oscilloscope architecture. I mean, how to use the oscilloscope in kind of in lab. You should know how the memory addresses. You can program what is JTAG, IJTAG. What are the protocols that you should know? All those things you should be very versed with. Hello.
Yeah, so I'm thinking like whatever I mentioned, it's like almost same, only oscilloscopes and JTAG it feel different. So I was expecting more answers for this, because there is a vast basic things that we need to learn, right? So I'm curious, that's what, like so before learning something more maybe an important domain, we should learn about the basics, then we'll be able to grasp easily, right?
So are you aware of the validation? I mean, VLSI topic that I have discussed till now, or you still have
Yeah,
questions?
so no, that one I have understood.
No, but you have understood, but were you aware of it
Yeah,
previously?
yeah. So I was aware of this.
So VLSI course as a student is 2 years, okay,
Yeah.
and validation is takes around 5 to 6 years for you to expertise. Now, what topics that you will cover depends on what application you wanted to go in, right?
Yeah. So actually, I have the book, that Introduction to VLSA, where the MTech people will study, right?
Yeah, but that doesn't. So do you expect that all the topics in that book will be covered? Then that's a unrealistic explanation
No, no,
expectation.
no. So that's what, before learning into the VLSA book, before start reading, we should know a basic. So where we'll have the computer architecture book that will explains the basic things before going to the VLSA, right?
So there are I would say physical design is more deeper subject than computer architecture, which is which every company has. DFT is for sure important. Every company will have. Verification is for sure important. There is no one book that will explain it. There are tens of books to understand it. But for sure, every company will have. Computer architecture, all companies will have. I doubt. So
No,
what I'm trying
no.
to say
So
is what.
actually, I'm not. Maybe I'm not mentioning about the teams. I'm talking about the basic topics. So you mentioned like computer architecture is not about the company teams, or no, not about that, right? So it's a basic thing a people should know about the computer architecture, like parallel processing or something like that. I'm asking.
So those are very high level topics. For a validation engineer, you need not to know the computer architecture. You can still work around it.
Okay.
You should know
So
how.
that's what, so the topics that a validator should know, like validation engineer should know.
So
What are the topics?
these are compiled together in the modules that Jasttech team has covered. Okay. So maybe
Okay.
you will get the brochure from the Jasttech team, and where the topics will be discussed. What are important as per my understanding and as per the Jasttech team that I expect. I am expected to answer. Okay.
Okay.
Yeah. Is there anything, Aswarya and Vinod, you want to ask?
Nothing
No.
from my side.
Great. So, yeah, we can conclude this meeting.
Yes, yes.